I'm going to be speaking about the I-squared statistic. Actually, since I met Carol at SRSM and we discussed doing this webinar, I was able to publish a paper called In a Meta-Analysis. The I-squared statistic does not tell us how much the effect size varies, and it's been published in the Journal of Clinical Epidemiology, and it covers a lot of the material we're going to be talking about today. At the end, I'll tell you how you can download a copy of that from the journal. We're talking about heterogeneity, and Ciprian actually sent me a number of questions that people had submitted in advance. They were very good questions, and they alerted me to some issues I might want to clarify. So first of all, before I even get started, when we're talking about heterogeneity, which is how much the effect size varies from study to study in a meta-analysis, there's always heterogeneity. If you define heterogeneity as the effect size being different in some studies than in others, if you're pulling studies from the literature, you can assume that the effect size differs from study to study. That's just the way the world is. So that's a given. But what we really are talking about is the clinical implications of heterogeneity. What does that mean for the utility of the intervention? So I think a good way to think about this, especially if we're dealing with clinical interventions like drugs or things of that sort, is to think about, from a clinical point of view, how much does the dispersion matter? And what I have over here is a slide. When we're talking about a random effects model, we're assuming that the effect size varies across studies. And here we're talking about a standardized difference in means between groups. So a value of 0 would mean that the two groups are equivalent. 0.5 would be a clinically useful effect, and so on. What we want to know when we ask about heterogeneity is, do the effects look like this? So the mean is something around here, and in all of the populations, this is meant to represent, this normal curve is meant to represent a distribution of effect sizes for all the populations in the universe that we care about. And in this example, I would say that the effect size is consistent in the sense that from a clinical point of view, the effect in any of these populations is pretty similar. It's always going to be an effect which is clinically useful and of moderate magnitude. So that's one possibility. Or does it look like this, where the mean effect might still be clinically important, but there's a lot of clinical dispersion around that, so that there are some populations where the effect is trivial and some where it is quite exceptional. This would be a second situation. And then the third is something like this, where there are many populations where the effect is helpful, but there actually are a non-trivial number of populations where the effect is harmful. So see, simply speaking about heterogeneity without context is kind of missing the point, because the heterogeneity here and here are both exactly the same. There's the same amount of spread, but the clinical implications are quite different. Over here, you might say we're going to go ahead and use the drug, and over here you'd be much more cautious and not want to use the drug until you can figure out where it's going to be helpful and where it's going to be harmful. One other point I wanted to mention, just to be sure that we're all on the same page, is that one common mistake that people make, generally when we look at a meta-analysis, which is displayed using a forest plot, there's this diamond down at the bottom, and the diamond represents the mean effect, and the endpoints of the diamond represent the confidence interval. Some people think that this confidence interval, the endpoints of the diamond, tell us something about the dispersion in effects, and that's completely incorrect. The confidence interval is an index of precision, not an index of dispersion. This speaks only to the mean, and the endpoints of the diamond tell us that the mean probably falls someplace inside this interval. It says absolutely nothing about how widely the effects vary. That is represented by this line over here, which we're going to be, and that's going to be a large focus today of how do we figure out how widely the effects vary and how do we communicate that information to others. Okay, so having said that, let me just give you a brief outline of the agenda. 5 points. First, I'm going to be talking about why we should not be using I-squared to quantify heterogeneity. The second, if we're not using I-squared, which is what people generally use, if we're not going to use that, how should we think about heterogeneity and what statistics should we use? And then, since the vast majority of papers actually do use I-squared, it's important to understand what it tells us and what it doesn't. The fourth thing, usually after I've gone through the first 3 items, people say, well, that's all good, but what happened when you forgot your wedding anniversary? And so I'm going to talk about that. And finally, I have some resources that you can use for meta-analysis in general, and particularly for heterogeneity. Okay, so the first item, why should we not use I-squared to quantify heterogeneity? I guess it's hard to get a show of hands on something like this, but I suspect that many of you have read meta-analyses in the past, and some of you have performed meta-analyses, and you probably know that the vast majority of papers in medicine and epidemiology especially, when they have to quantify the amount of heterogeneity, they use a statistic called I-squared, which goes from 0% to 100%. And in many cases, they classify the amount of heterogeneity based on the value of I-squared. For example, they might say that an I-squared value of less than 25% means that there's a low level of heterogeneity, 50% is moderate, and 75% is high, or some other classification system. I want to show you that I-squared should not be used at all to quantify heterogeneity. And because it's so common, people, when I first, mentioned this topic, people think that, what could he possibly be talking about? I want to sort of shock you out of your complacency by showing two examples. This I'm calling example one, and this is a paper that was published, I think, in BMJ, and I'm going to call it the off-hour analysis. And what happened over here is patients coming into a hospital with a myocardial infarction. In other words, patients that have a heart attack and they're brought into a hospital by ambulance. Some of them arrive during the day, obviously, and some arrive in the middle of the night. And we have about 20 or 30 studies over here, and they all did the same thing. In each study, they went to a hospital and they compared the risk of death for patients who arrived in the middle of the day versus patients that arrived in the middle of the night. And it turns out that the mean effect size is an odds ratio just slightly greater than 1. On a slide like this, anything to the right of 1 would indicate that patients were more likely to die if they arrived at night. Anything to the left would mean they were more likely to survive if they arrived at night. So the odds ratio was slightly greater than 1, and on average, patients that arrived at night were more likely to die, but it was a small effect. The question now is, what does the distribution of effects look like? If it looks something like this thing over here, I have A, B, and C, which are 3 possible distributions. In all of them, the mean is exactly the same. I think it's an odds ratio of 1.06, but they vary in dispersion. So if it looks something like this would basically, the take-home message would be that patients that arrive at night have a slightly increased risk, but it's not a major increase in risk, and there's probably not a lot that we can do about it. On the other hand, if the distribution looks like this, or even like this, let me just skip to C to save some time. Here we have the same mean of 1.06, but it turns out that there are some hospitals where if you arrive at night, your chances of surviving, your chances of dying are cut in half compared to if you arrive during the day. And there are other hospitals where if you arrive at night, your chances of dying are double what they would be if you arrived during the day. If that's the case, then the mean becomes largely irrelevant. What we need to figure out is what distinguishes these hospitals from these. For example, it might turn out that in these hospitals, they have a cardiac staff, they have a cardiac team in the hospital all night long, and so they're able to get to the patients quickly, whereas in these hospitals, they don't. So if it turns out that's the case, that would then give us a lead on perhaps how to change the way that hospitals do their staffing and so on. So the question is, which one of these distributions is the one that actually is seen in the data? And so the paper reports that they looked at this, the I-squared, and the way that they gauged heterogeneity is by using the I-squared statistic, which turns out to be 75%. They said on that basis, heterogeneity is high. Okay, so basically they said we're talking about something like this. Okay, so I want to do a quick poll. Ciprian said you could help me with this. Based on this, do you think that the distribution of, so they decided, the authors decided that this represented high heterogeneity. Do you think that the actual distribution looks like A, B, or C? Let's take 20 seconds to lock in your votes. Okay, great. So we have 57% that said C, 28% that said B, and I think it's 15% that said A. In my experience, I've done this quite a few times. Generally, I get about 80% of the people saying C, about 15% saying B, and about 5% saying A. And we got something comparable over here, although I'm going to give myself some leeway because the title of the talk is you can't use I-square to quantify the amount of heterogeneity. The actual answer is A. And I was one of the people that voted for A, so I guess, that actually bumped that up a little bit. So, that probably is not what people are expecting to see. I think the larger point is that you have to imagine if there's a group of people sitting around in a hospital trying to set policy, and they're doing that, based on what we're seeing over here. They're trying to decide, not to set policy, but they're trying to decide whether or not it makes sense to pursue this as something that might save lives. And they're reading this, and they know that I-square is 75%. Some of them think that the distribution looks like this. Some think that it looks like this, and some think that it looks like this. And so they're trying to set policy based on three different understandings of what the data actually tell them. And of course, there's the additional irony over here that most of them think that it's this or this, when in fact it's this, which is indicated over here by the check mark. Let's take a look at one more example. I'll call this example 2. This is an analysis that looked at two strategies for treating patients. These are patients that are in the hospital, they're in danger of dying, and they are candidates for a blood transfusion. Now, there are risks and benefits associated with a liberal strategy and a conservative strategy. A liberal strategy means that you give them the blood transfusion as soon as possible, which might save their life, but it also might kill them. And the conservative strategy is that since you don't want to do any damage, you're going to wait until they're pretty much on death's door before using the transfusion. So you're basically, and the question is which one of these is actually more likely to save their life. Now, again, in this case, you can imagine A, B, or C. If it turns out that it's A, then really, in this case, the mean odds ratio is essentially 1. There's no difference between them. But if the distribution looks like this, then basically there's no population where either one of these is going to be better. On the other hand, if it looks like this, there are some populations where the conservative strategy is going to reduce the risk of death by close to 40%. And there are other populations where the liberal strategy is going to reduce the risk of death by roughly 50%. So it would be imperative to pursue this and figure out which populations are here and which ones aren't here. In this case, they reported that the I-square is only 29%, and so heterogeneity is low. Okay, again, if we can do a quick poll, do people think we're talking about A, B, or C? And this is called heterogeneity is low. So, but I mean, you're getting the idea. Most people are now shifting. I have close to half of you said C because you've discovered that I'm not trustworthy. 27% still said A. The answer over here, of course, is going to be C. This is the one where heterogeneity was classified as low. So at a minimum, even for those of you that got this right, I'm hoping you're beginning to be shocked out of your complacency and recognize that using I-squared to classify heterogeneity is probably not a foolproof idea. Just to show the two of these side by side, this is the one where I-squared was 75%, and it looks like this. This is the one where I-squared was 29%. And we actually have about 3 or 4 times as much dispersion here as we did here. And certainly, if we simply classify this as high versus low, this would be called high, and this would be called low. So what's going on over here? Okay, I'm going to circle back to I-squared in about 10 or 15 minutes. But before I do that, I want to talk about how we should be thinking about heterogeneity, not what people actually do, but what they should be doing. And I'm going to, as a motivating example, I'm going to use this study, which is called Efficacy of Methylphenidate. This is a paper that was published by Castells et al. And the basic idea is this. There were 17 studies. People, I'm sure, are familiar with attention deficit hyperactivity disorder, or ADHD. People that are diagnosed with this have trouble concentrating, and therefore they have trouble performing at work. And what happened in these studies were half the patients were randomized to get a drug, which is called methylphenidate, like Ritalin, and half were given a placebo. And then at the end of the study, they compared the cognitive function of the two groups. And it turns out that the mean effect size was 0.5, which would be considered a moderate effect. We're talking here about a standardized difference in means, and the mean effect size was 0.5. For context, an effect size in this range might be considered trivial, and in this range might be moderate, and in this range might be large. So what does the distribution of effects look like? Does it look like this? In which case, most of the in most of the populations, the effect size falls between 0.4 and 0.6, or does it look like this, or does it look like this? So which of these is true? How do we decide which one of these is the case, and how do we then communicate it to others? And the answer is we would do the same thing that we do in a primary study. I have over here a fictional study. These are kids that are in grade school. We want to know how well they're doing on a math test, so they all take a test. It turns out the test has scores that go from 0 to 100. The average score on the test is 50. And the question then would be, what does the distribution of effects look like? Well, how do we report it in a primary study? The answer is we give the mean and the standard deviation. So if I report that the mean is 50 and that the standard deviation is 5, I automatically understand that most students fall in the range of 40 to 60. How do I know that? Because if the effects are normally distributed, then most students are going to score within 2 standard deviations of the mean. The mean minus 2 standard deviations gives me 40. The mean plus 2 standard deviations gives me 60. So I understand that the distribution, the endpoints of the distribution are going to fall, more or less over here, and that the whole distribution is going to look something like this if it follows a normal curve. This line over here, 40 to 60, is called a prediction interval. Why? Because if somebody came into the class and they said, I'm going to pick one student at random, and I'd like to know what her score is going to be, what do you think it's going to be? I would predict that she's going to score someplace between 40 and 60, and I'd be correct roughly 95% of the time, because 95% of the students will fall within that range. So similarly, if I reported that the mean was 50 and the standard deviation was 10, I automatically understand that corresponds to a prediction interval of 30 to 70. Or if I report that the mean is 50 and the standard deviation is 20, the mean minus 2 standard deviations gives me 10, the mean plus 2 standard deviations gives me 90. So the way that I compute the prediction interval is simply to take the mean plus or minus 2 standard deviations. And the way that I report it is the same way. As a matter of fact, I have the option. Generally, people simply report the standard deviation. But the reason the standard deviation works, there's nothing intuitive about the standard deviation as such, but it serves as a handy shortcut, because since we understand statistics and we're familiar with the normal curve, if somebody says that the standard deviation is 5, in my head, sort of without even thinking about it, I automatically understand that the kids are going to score in this range, because hearing the standard deviation, I can automatically intuit what the prediction interval looks like. But what really matters over here is the prediction interval. That's the endpoint. The standard deviation is really an interim step in getting to that. So how do we do heterogeneity in a meta-analysis? Well, we would do exactly the same thing. In the ADHD analysis, for example, if I report that the mean is 0.5, and we can compute the standard deviation of the effects, and if that turned out to be 0.05, I could report that the mean is 0.5 with the standard deviation of 0.05. And then if I figure 2 standard deviations below the mean gives me 0.4, 2 standard deviations above the mean gives me 0.6. So in 95% of all comparable populations, the effect size is going to fall someplace in this range. Similarly, if I report that the mean is 0.5 and the standard deviation is 0.1, I understand that in 95% of populations, the effect size will fall someplace between 0.3 and 0.7. And if I report that the mean is 0.5 and the standard deviation is 0.2, I understand that in 95% of populations, the effect size will fall someplace between 0.1 and 0.9. And then again, assuming a normal distribution, we can get a sense of what the whole distribution looks like. Again, this range over here, 0.1 to 0.9, is called a prediction interval, because if somebody says, I'm planning to go into this universe of populations and pull one at random, what is the impact of methylphenidate going to be in that population? I'd say, well, it's probably going to be someplace between here and here. And again, assuming that my numbers are correct, I would be correct 95% of the time, because in 95% of populations, the effect size actually will fall in that range. Once again, how do I communicate this? Well, I can report the mean and the standard deviation. I can say that the mean is 0.5 with the standard deviation of 0.20, hoping that people will then figure this out. Or I can skip the interim step. I can simply give them the prediction interval. I can say that the prediction interval is 0.1 to 0.9, because again, the standard deviation is only an interim step. It's really the prediction interval that we care about. The reason I'm making that point is that it turns out that in a meta-analysis, there are many times when you can't actually compute the standard deviation, but you can compute the prediction interval. And so you can sort of bypass the interim step and jump right to the end. But as long as you have the prediction interval, that's actually what you need. Let me show you what this looks like. I'm going to open this up in comprehensive meta-analysis. This is a program that we developed. I'm going to go to run the analysis, and the analysis screen looks something like this. I can sort this from low to high, so I get a general sense of the dispersion in effects. It looks like there are some effects as low as minus 0.2 and some as high as 1.3. But for many reasons, this is only to give us a very general sense of the dispersion. This is not accurate in any way. What we really need to do is to compute the standard deviation and the mean. If I go over here to next table, I can see that the mean is roughly 0.5. The standard deviation, which is called tau in a meta-analysis, is 0.197. If I round that to 0.2 and I take the mean plus or minus 2 standard deviations, I get the mean minus 2 standard deviations is roughly 0.1. The mean plus 2 standard deviations is roughly 0.9. So I figure that the prediction interval is going to be roughly 0.1 to 0.9. The program actually computes the prediction interval for me, and it says that it's 0.06 to 0.95. The reason it's not exactly 0.1 to 0.9 is because it makes some adjustments. I'm not going to go into them right now, but it makes adjustments for the error in estimating the mean and for the error in estimating the standard deviation. And this is the more accurate interval, 0.05 to 0.94. If I now go back to the table, you can see what we're able to do over here is to actually include the prediction interval in the plot. And just to be clear, I mean, I'm happen to be using the program that we developed. You can do the same thing in R. You can do the same thing in Stata. All of the major programs now allow you to compute and display the prediction interval because it's become increasingly clear how important this is, and more guidelines are asking people to do it. We can do one more thing in CMA, which is we can actually plot the distribution of effects. So for example, over here, if I say plot the effects, I get this whole plot, which tells me that, okay, the mean is over here, and this is the confidence interval, so the mean probably falls someplace in this range. But as far as the dispersion in effects, the prediction interval is 0.06 to 0.95. That corresponds to 0.06 and 0.95. And we also get the whole distribution, similar to the plots that I was showing you a minute ago, which gives us a more nuanced view of what proportion of the populations fall in the moderate range, or in the large range, or in the small range. And finally, you can also generate a report, which looks something like this. I'm not going to go through the whole thing, obviously, but if we come down here to the statistics for tau and tau square, it says tau, the standard deviation of true effects is 0.197, and then critically the prediction interval. If we assume that the true effects are normally distributed, we can estimate that the prediction interval is 0.058 to 0.954. The true effect size in 95% of all comparable populations falls in this interval. So that's the basic idea. Also, if we go and generate a high resolution plot, which looks something like this, we'll see down at the bottom, again, we have the confidence interval and we have the prediction interval. So that's the basic idea, how you compute the prediction interval and how you display it. Let me close this for a second. And okay. Okay, so the basic idea then is in a primary study, what we do is we compute the prediction interval using the mean plus or minus 2 standard deviations, and we can do exactly the same thing in a meta-analysis. When I'm teaching this in person, at this point, I generally get two reactions. For people that are not familiar with meta-analysis, they say, so what's the big deal? Why are you wasting our time? Basically, what we're doing over here is the same thing we've been doing forever. Why spend any time on this? On the other hand, for people that have done meta-analyses and that are familiar with I-square and the Q-value and the P-value and tau square and all of these things that people typically report, they say, well, this can't be right. I mean, what you're presenting is basically very simple and straightforward. If this was true, why are people coming up with all of these statistics that really don't make all that much sense and reporting them? You must be missing something. So The reason that we need to talk about this, I think in a perfect world, we pretty much could stop over here and just focus on the prediction engine. The problem is that almost nobody uses it, and people do use these other things. As a matter of fact, I did a sort of a quick survey of papers published in the British Medical Journal going back over several years. Roughly 80% of them report I-square and use that to quantify the heterogeneity, and less than 3% use the prediction interval. So clearly, what I'm talking about over here is not generally accepted, although it's becoming more and more understood that this is an important thing to do. So what is I-square? I sort of have to inoculate. I can't simply tell you that it's not useful. I gave you 2 examples to show that, but the purpose of this, one of the purposes of this webinar is to explain what I-square actually is. And once you understand it, you can understand how people are misusing it. Just to be clear, there's nothing wrong with the I-square statistic. It's a completely valid and useful statistic when used as intended. The problem is it was never intended to be used in this way. To explain what I-square is, I have to talk about true effects versus observed effects. In a primary study, in the example we were using before with these children, each kid gets a score on the test, and we assume that whatever score the kid got, that is that kid's true score on the test. We treat the observed score as the same as the true score. By contrast, in a meta-analysis, in any study, we have an effect size. The effect size is the observed effect, but we also have what's called the true effect. For example, if one of the studies was done in a hospital and the population was all the people enrolled in the hospital, and the sample is the 20 or 30 or 50 people we happen to include in our sample. The effect size that we see in our sample is the observed effect. The true effect would be the effect that we would see if we could somehow enroll the entire population of the hospital in our study. Of course, we can never do that. So we use the observed effect to estimate the true effect. It's the best value that we have, but it's always going to be either an underestimate or an overestimate. As it turns out, since we have 2 effects, we have the observed effects and the true effects, you actually can think of having a distribution of observed effects, and which we can see, and the distribution of true effects, which we can't see, but we can only make inferences about. For reasons that I'm not going to get into right now, the distribution of observed effects, the one that we see, tends to be greater, wider than the distribution of true effects. I mean, I said I'm not going to get into it, but just in general, the idea is that whatever the distribution of true effects looks like, the distribution of observed effects will tend to be wider than that because it incorporates the true variance, the actual variance of the true effects, plus additional variance that's due to sampling error. So if there's only a small amount of sampling error, then the distribution of observed effects will be a little bit wider than the distribution of true effects. But if there's a lot of sampling error, the distribution of observed effects might be a lot wider than the distribution of true effects. So if the observed effects look like this, and this is basically what we would get if we plotted the observed effects, it's possible that the true effects might look like this. It's also possible that they might look like this, or like this, or like this. And it's even possible that they might look like this. In other words, you can imagine a situation where the true effects actually don't vary at all, but the observed effects will vary quite a bit. And remember, what's always true is that we're looking at the observed effects, which is shown in blue, and we're trying to infer what the true effects might look like. And these are 2 separate distributions. Once we recognize that, it becomes obvious that there are 3 distinct questions that we might ask about the distribution of true effects. First of all, we might ask if the true effects vary at all. In other words, we're looking at the blue distribution. Is it possible that if we could actually see the distribution of true effects, that it would not be a distribution at all, but that the true effect size is identical in all the studies? That's one question. That's addressed by the Q statistic and the p-value. If we do a test for heterogeneity and we get a p-value that is statistically significant, we can say we have empirical evidence that the true effects are not all identical to each other, but they vary at least a little bit. A second question we can ask is, well, we have this distribution of observed effects, and we're making an inference about the distribution of true effects. What's the relationship between the 2 of these? What's the ratio of this distribution to this one? And that is what's being addressed by I-squared. I-squared tells us what is the ratio of true to total in squared units? So that's the second question we can ask, and that is the statistic that would address that. The third question we can ask is, how much do the true effects vary? In other words, what is this point over here, and what is this point over here? In this case, the answer would be that the effects vary from 0.1 to 0.9, and that is given by the prediction interval. So the key thing is, there are three questions we can ask. Each of them is a valid question, and each of them has a statistic that addresses that question, but the questions are not interchangeable, and the statistics are not interchangeable. If we want to know, what's the ratio of one to the other, the question that the statistic that addresses that is I-squared. If we want to know how widely the effects vary, the statistic that addresses that is the prediction interval. But if I want to know how the effects vary, the answer has to be 0.1 to 0.9. It can't be 47%. You can't take one answer and apply it to a different question, okay? So at this point, as I said before, the question that people ask is, okay, well, that's all very interesting about the three questions, but what happened when you forgot your wedding anniversary? And I'm going to answer that now. I'm going to skip the beginning because it's not pretty. You really, having heard the details, you're never going to be able to forget them. But a couple of days later, I found myself in a jewelry store. I found myself actually in the Neiman Marcus department store in the jewelry department. And I was looking for a string of pearls. I walk in there. The salesperson said, well, we were expecting you. Your wife has this very nice set of pearl, a necklace made out of pearls that she thought you might be interested in having a look at. There were three questions I can ask the sales lady. I can say to her, is the cost zero? In other words, is it free? Is the amount of dollars that I'm going to pay zero? In which case she probably would say no. She might also call security, but she certainly would say no. So it's a valid question, and that's a valid answer. The second thing that I can do, actually, she said to me, we're going to give you a discount because we know your wife and she's a very nice lady. I could have said to her, of what proportion do I pay? In other words, of the amount that regular people pay for this, how much of a discount would I be getting, or what proportion would I be paying? And she might have said 50%. Again, it's a perfectly reasonable question and it's a perfectly reasonable answer, but it's not the information that I need. What I really wanted to know is how much am I going to be paying? So I might say to her, well, how much do I pay? And she might say $5,000. Okay, again, three completely legitimate questions and three completely legitimate answers, but they're not interchangeable. So why is this relevant over here? Well, the analogy to a meta-analysis is this. In the case of a meta-analysis, I can ask if the effects vary at all. In other words, if the amount of variance is zero. And in the case of the jewelry store, I can say, is the amount of dollars zero? These are both valid questions. They're valid answers, but they're not very interesting. Why are they not very interesting? Well, in the case of the jewelry store, I pretty much know what the answer is going to be. And in the case of a meta-analysis, if I pull studies from the literature that are looking at the impact of an intervention, and the question is, does the effect size vary at all from study to study? The answer is, of course it does. There's no intervention that's going to have exactly the same effect in two populations. It's a ridiculous question, and it's a valid answer to a question that nobody really cares about. The second thing is that in the case of the jewelry store, I can ask the person what proportion I'm going to pay. And in the case of the meta-analysis, I can say, of the variation that I'm seeing, what proportion is real? This actually is an interesting question. I'd like to be told that I'm getting a discount. I'm not paying 100%, I'm paying 80% or 50%, but it still doesn't tell me what I really need to know, which is, how much do I have to pay? And the third thing is, in the case of the jewelry store, I can sort of bite the bullet and say, well, what is this actually going to cost me? And she's going to give me a number. And in the case of a meta-analysis, I can say, well, how widely do the effects actually vary? And this is actually what I wanted to know when I asked about heterogeneity. Eureka, okay? Now, the fact of the matter is, in the jewelry store, I kept asking her, how much do I need to pay? And she kept saying, well, you're getting a discount. She didn't want to actually give me the answer. So she was sort of pushing this on me, what the discount was. Similarly, in a meta-analysis, papers don't give you the prediction interval. They sort of push I-square on you, which is exactly what this woman was doing. In her case, I think because she didn't want me to faint. And in the case of a meta-analysis, because people don't know any better. But here is where this analogy really becomes crucial, because there's one critical difference between the jewelry store and the meta-analysis, which is this. In the store, when I said to her, how much do I need to pay? And she said, only 50%. I'm not going to write a check to Neiman Marcus for 50% because I know that's not going to fly. If I try paying them with that check, again, you know, the security people aren't far away. They've already been called when I asked if it was free. You know, they're there and ready to escort me out of the store. So I'm not going to do that. I'm going to say to her, that's not the information that I need, because the fact that I'm paying only 50% is not useful. If the cost is $100 and I'm paying 50%, I'm paying 50. If the cost is $1,000, I'm paying 500. And if the basic cost is $1,000 and I'm paying 50%, I'm paying 5,000. This is the information that I need. This is not adequate. By contrast, in the case of a meta-analysis, if I say, what is the range of effects? And somebody says to me, well, it's 50%, people somehow think that they understand what that means, when in fact, they don't. The fact that I'm paying only 50%, if the observed effects look like this, 50% of that might look like this. If the observed effects look like this, 50% might look like this, and the same for this one over here. What I need to add, I can't, but the problem is I can't simply accept I-square. I need to ask for the prediction interval, and that's what I have in mind when I ask about heterogeneity, and that's the information that I need. Okay, at this point, people, let me just ask you, how tight are we on the time? It looks like it's a quarter up. Do I have to stop directly at 4, or can I go over? Can anybody hear me?
Yeah, you can go over, no problem.
How far can I go over?
Do you want, how much time do you want? Like, we'll need about, I don't know, 7 minutes for questions?
Okay, can I go, let's say, until 4:15?
No, well, we would like to go over some questions. So maybe we could take questions now, Michael, and then we can go over after that, and whoever can stay can stay.
Let me proceed a little bit more, and I'll try to skip over parts that I can. At this point,
okay.
People sometimes say, you know, seriously, you know, basically what I'm saying is that what people have done in tens of thousands of analyses is incorrect, and what you should be doing is just incredibly simple.
Sorry, Michael, a bunch of people have said that going over is fine, so why don't you just go ahead?
Okay, thank you very much. So people say, you know, seriously, I mean, basically what I'm saying is that tens of thousands of meta-analyses have been done incorrectly. And the actual solution is incredibly simple. And they say, you must be doing something wrong. In fact, you know, they say, well, what do we actually know about you? I mean, the only thing we know about you for sure is that you couldn't even remember your own anniversary. Oh, by the way, I wanted to show you. Can you see this? This is Neiman Marcus, and here, my wife loaned me these for today. Here are the pearls. It's actually quite nice. I think. Okay, but they say, you know, this can't possibly be right. So as it happens, I was teaching this course a couple of years ago in London, and I told people pretty much the same thing I've told you here. And a gentleman in the first row got up and started screaming at me. He said, "You have no idea what you're talking about," and then he stormed out of the room. Well, as it happens, my good friend Julian Higgins, who created the I-squared statistic, this is the original paper written by Julian Higgins and Simon Thompson, happened to be in town for a conference. And I asked him if he wouldn't mind coming to the workshop the next morning. And again, I asked this fellow to stand up and yell at me, which he did. And then I asked Julian to take the podium. And I'm just going to show you a quick clip of that. You know, wouldn't it be nice, you know, if life was actually like this? So what I have over here in the back is Julian Higgins, the creator of I-squared. Stand over here. Yes, no, over here. Yeah.
So you want to say something? Basically, Michael is right. We always portrayed it
Okay, so Julian went on to speak for about 20 minutes, and it was really fantastic. But basically, there's no daylight between his position and mine. As a matter of fact, he's the one that alerted me to the fact there was one point when I was making the same mistake about Isquared when we were working on our book, on which he was a co-author, and he said to me, Michael, you don't get it. Isquared does not tell us how much the effect size varies. And then I sort of, hit myself upside the head and remembered that I was falling into the same trap as everybody else. Isquared is defined as a proportion. It's the ratio of the true variance to the total variance. People sometimes see it in this format, which might not be that clear what it is, but basically this is what it comes down to. It's a ratio of true to total, which is not the same as an absolute value. So coming back to the first two examples, just to give you some closure on that, in this case of the Offhour presentation, where we said that Isquared was 75%, the fact that Isquared is 75% is compatible with any one of these. If the dispersion of effects had looked like this, 75% of that would give us this. If it looked like this, 75% would look like this. And if the observed effects look like this, 75% of that would look like this. As it turns out, the observed effects look like this. 75% of a very narrow interval is still a narrow interval. If you actually look at the file, you can see what this looks like. I'm going to sort this from low to high. You can see that all of the effects, these are the observed effects we're looking at over here, all fall within an incredibly narrow range of the mean. There's virtually no dispersion at all in the observed effects. And therefore, if you plot the prediction interval, you can see it down here. It's very narrow. It goes from 0.97 to 1.15. Oh, no meaningful dispersion. If you want to plot that, it looks something like this. You can see how narrow the dispersion is, okay? By contrast, let me just close this. When we move on to the second example, the transfusion analysis, they reported that I-squared was 29%, which is correct, but the idea of classifying that as low is assuming that it tells us anything about the amount of dispersion is wrong, because again, an I-squared value of 29% is compatible with this, this, and this. It simply tells us that of the variance that we're seeing, only a small fraction of that is real. As it turns out, the amount of variance was very large, and 29% of a very large amount can still be a large amount. Again, if we go back and look at the actual distribution of effects, I'm going to run the analysis. You can see over here, I'm going to sort this from low to high to give you a better sense of it. Look at how widely the effects vary. There are some effects where the odds ratio is 0.17 and some where it's 11. So you take 30% of that and you still end up with a distribution that looks something like this, very wide. So that's why all of this makes sense. Okay, and just to show you the two of them side by side, this is the one where they said I-squared was 75%. This is the one where they said it was 29%, and that sort of explains what's going on. And it explains, so first of all, simply using I-squared, even without classifying it, is not going to give you useful information, and it sometimes will be very misleading. When they take it one step further and call this high and call this low, you can begin to see how this really does not work at all. On the other hand, if you simply report the prediction interval, you're giving people the information that they need in a format which is clear and concise. You say that the effect always falls in the range, almost always falls in the range of 0.96 to 1.17. People know what that means. There's no room for confusion. This is actually the information that people have in mind when they ask about heterogeneity. And of course, the same thing applies over here. There are some caveats to using the prediction interval. I'm not going to go into them in great detail. They're all listed in the paper, but the main ones are that you need a sufficient number of studies in order to estimate the prediction interval reliably. You might use 10 as just sort of to give you a sense of scale, and also that in computing the interval, we assume that the effects are normally distributed, which might not always be the case. There are ways of dealing with that, which I talk about in the paper, but you have to be aware that you have to sort of be humble in interpreting this. Just for some context, I have just one more example that I want to share with you. This is a paper on the use of tocilizumab for COVID-19. It's a paper that was published recently in Medical Virology. They looked at 23 studies where patients that were hospitalized for COVID-19, they were all given the standard of care, but half of them were additionally given this drug, which I'm just going to call Tosil. And it turns out that the risk of death was lower for patients that were given the drug. The difference in risks was minus 0.06, which means that it lowered the risk of death by 6 percentage points. It was a very narrow confidence interval, and the p-value for that was 0.03. So the take-home message from the abstract and the paper is that the use of this drug is associated with a decrease in the risk of death. And obviously, since this was done early on and patients were dying at a tragic rate, this was a very important finding. What about heterogeneity? Well, they reported heterogeneity was evaluated using the I-squared statistic as defined in the Cochrane handbook. The I-squared value was more than 50%, which was considered substantial heterogeneity. So the bottom line, when they say that there was substantial heterogeneity, that's not actually a meaningful term. Well, first of all, because it was based on I-squared, we don't know what it looks like, but let's assume for the sake of argument that there was substantial heterogeneity, which it turns out from a clinical point of view, there actually was in this case. But people don't have any idea what that means. I mean, does it mean that the effects were always that the treatment was always associated with a decrease in the risk of death, but it varied, from 2 points to 10 points? Or, does it mean that it was sometimes harmful? They themselves don't have any real idea of what that means. And therefore, they can't really talk about it in the analysis. And the focus is simply on the mean. And on average, this was associated with a drop in the risk of death. So let's actually open up this data set and look at it over here. We're looking at a difference in means. I'm going to change the scale so that it goes, let's say, from, okay. So on average, the risk of death was reduced by 6 percentage points. The confidence interval excludes the null, which would be 0. The p-value is 0.032. And that was the take-home message of their paper, along with the fact that I-squared was 80%, which meant high heterogeneity. So in this case, I would actually agree that there's high heterogeneity, but the point is they have no concept of what that means from a clinical point of view. Look what happens if you look at the prediction interval. It's clear that in perhaps 30% of populations, this was actually associated with an increase in the risk of death. In fact, if I go ahead now and plot that, the plot looks like this. The nil effect is 0. In roughly 30 or 35% of populations, this is associated with an increase in the risk of death. And what you can then do is send this over to PowerPoint or Word or something and annotate it. And when you do, it looks like this. In these populations, the treatment was associated with a decrease in mortality. And in these populations, it was associated with an increase in mortality. If you actually understood this, the take-home message would no longer be that this is effective on average. The take-home message would be there are populations where this might help you, and there are populations where this might kill you. These were observational studies, so I guess it would be more accurate to say it was associated with an increase, with a decrease in mortality or an increase in mortality. But the thinking is, I mean, this was actually making a difference. That was sort of the conclusion that they were trying to draw from this. And now the take-home message would be, don't use this with everybody. The key thing is to figure out which patients fall over here, which patient groups are over here where we would want to use this, and which patient groups are over here, which we would absolutely not want to use it. And in fact, if we can figure that out for the patients where it's effective, the impact might no longer be, 0.06. It might shift all the way over here. You might be able to reduce mortality by much more than 6 percentage points. And obviously for patients where this is harmful, you don't want to use it at all. I taught this in a workshop a couple of weeks ago. We actually had a cardiovascular surgeon in the class, and he explained to me in great detail why this makes sense from a biological or a clinical point of view. I don't have time to go into that now, but the point is people were not looking for that because they were focusing on the mean. And this is one example of why it's so important, so incredibly important, to not only talk about how much dispersion there is, but from a clinical point of view, where that dispersion lies. Now, I said earlier that we could compute the prediction interval simply using the mean plus or minus 2 standard deviations. I meant that as a conceptual definition of the prediction interval. But in reality, you need to use software for a number of reasons. One of them being that this will not work. This idea of the mean plus or minus 2 standard deviations will not work at all if you're dealing with ratios or prevalence or incidence. It only works for a standardized difference in means and a risk difference. And another thing is you want to actually adjust the interval to account for error. And so you always want to use software. Now, fortunately, the formula to compute the prediction interval and to include it in a plot is now available in the most recent release of Stata. It's available in R. And as I showed you, it's available in our software, which is called Comprehensive Meta-Analysis, or CMA. Additionally, we now have free standalone software. CMA is a commercial package. But what we've done is on our website, we've put a free software, let me see, that you can download. You don't need a license for it or anything else. And it looks like this. You open it up, and you have to choose what kind of an effect size you're using. In this case, I would say the risk difference. You enter data, you enter the mean effect size, the upper limit of the confidence interval, tau squared, and the number of studies, which you can get from R or Stata. You can also get that from RevMan, which is important because RevMan will not, as far as I know, compute the prediction interval. And once you've entered those 4 pieces of data, you simply click next, and the program generates the plot. You can then send it to PowerPoint, annotate it, and so on. So that software is absolutely free. And as I said, it can be used with any other software. So that's one item I wanted to call your attention to. If we have 2 websites, one of them is called metaanalysis.com, and the other is called metaanalysisworkshops.com. If you go to either of those websites and scroll down a little bit, you'll see these 4 buttons over here. One of them says, send me the common mistakes in meta-analysis book. If you click on that, this server will send you a copy of this book. It's about 400 pages. It'll send you this as a PDF, and it includes about 80 pages on heterogeneity, discussing everything that we've discussed here, but in much more detail. It also deals with mistakes in choosing a statistical model, in assessing publication bias, and many other things, and it's absolutely free. If you click on this button that says send me the prediction intervals program, it will send you the program that I showed you just a second ago. And if you click on the button that says download a paper, download the paper on Isquared, it will give you a link to actually download this from the Journal of Clinical Epidemiology. And there's one other thing. You sent me a number of questions that people had submitted earlier in the week. And one of the questions was where can we get more information on this? Are there any videos about this, and so on? And it occurred to me, we have an online workshop where I have about 14 hours worth of videos about this, and I figured why not just give everybody free access to the workshop. So that's what I'm going to do. If you want to send me an email at this email address, bios.100@gmail.com, I've arranged for my office to sign you up with a free access to the workshop, where you will have access to these 14 hours of videos. Additionally, one thing we do in the workshops, we have these weekly Zoom sessions, and I'm going to try to get to a number of questions right now since we have a little bit more time, but we can continue this conversation over Zoom. Anybody that wants to do that, just send me an email. We'll sign you up for the workshop. You'll get a link, and then we can go over these questions in detail next week, the week after, and so on. I want to call your attention to a couple of other papers about this. One of them is Basics of Meta-Analysis. Isquared is not an absolute measure of heterogeneity, and Julian actually was a co-author on this. And then there are other papers as well. I should be clear, I'm not the only person sort of beating the drum about this. There are other people doing the same thing. One last thing. I mentioned before that people sort of think, well, if there are tens of thousands of papers out there that use Isquared, there must be some validity to it. I'd like to draw an analogy to p-values. As I'm sure all of you know, for 50 or 60 years, virtually all papers reporting the results of clinical trials focused on a p-value, and people would then use the p-value as a surrogate for the effect size, when in fact there's really no good reason to do that. And this happened despite the fact that there were hundreds of papers explaining that it's a mistake, and books, and so on. The point about p-values is they dominated papers for more than 60 years. They still actually do. They are misinterpreted in virtually all cases, but they're valid when used as intended. In other words, if you actually use a p-value to test an hypothesis, that's a valid use of the p-value. The problem is not that the p-value is wrong, but that people misuse it. They use it as though it tells us how large the effect size is, when that's a mistake. Similarly, Isquared has dominated papers for, at this point, close to 20 years. In virtually all cases, it's misinterpreted. People interpret Isquared as telling us how much the effect size varies, when in fact it does not. That is not an indictment of Isquared. When we use Isquared to tell us the ratio of truth to total, which is the way it was meant to be used, it's a perfectly valid statistic. The problem is not with the statistic, the problem is with the fact that people are misusing it. And over here I have a picture of three people. People sort of look at this, they say, wow, that, just three very handsome people. That's true, but that's not the reason I'm showing it. This over here is Ronald Fisher, who invented the p-value, Julian Higgins and Simon Thompson, who invented the Isquared statistic. Ronald Fisher was a genius, as are these two people. They really are. But people say, well, the p-value is wrong. The p-value is not wrong. It's simply being misused. And similarly, I do not mean to imply there's anything wrong with Isquared. The problem is not with the statistic, it's with the way it's being used. And finally, just one more thing, in these 50 or 60 years that people have sort of been beating up on the way the p-value is being misused, this fellow over here, David Bacon, said that using the p-value in that way is a kind of essential mindlessness in the conduct of research. And this person, Jeffrey Loftus, said, I find it difficult to imagine a less insightful means of transiting from data to conclusions. And finally, my mentor, Jack Cohen, said, I think, and this is the most critical one, the p-value does not tell us the size of the effect, but we so much want to know the size of the effect that when somebody gives us the p-value out of desperation, we take that and push it into use as a surrogate for the effect size. I think that's exactly what's going on over here. If people want to know how much the effect size varies, if they're given the prediction interval, they're going to use that. If they're given Isquared, they're going to push that into service as an indicator of heterogeneity, when in fact that is a serious mistake. It was never meant to be used in that way. Okay, I'm now going to come to questions and answers. There were three or four questions that were submitted in advance. Carol, Ciprian, do you want me to just begin with those, or do you want to take over now?
Yes, please, start.
Oh, okay. Sorry,
start with this, yes.
Okay.
Yeah, can you? Yeah, definitely. Thank you.
Okay. So the first question was from Benjamin Rouse. I hope I'm pronouncing that correctly. And he said, rather than the prediction interval, could researchers use TOR directly to evaluate heterogeneity? And the answer is, in some cases you could, but I think it's better intended as a conceptual definition rather than actually using it. So for example, in the methylphenidate case, as I said before, we could in theory take 0.50 plus or minus 2 TOR to get an estimate of the dispersion. But there are three reasons that we don't want to do that. The first reason is that when you simply compute the dispersion, which in this case would be 0.2 times 2, so 0.4 to the left of the mean, 0.4 to the right of the mean. So you're saying that the effects vary over 80 points. You're talking about the dispersion as an absolute value. You're simply saying the effects vary by 80 points. Whereas if you compute the prediction interval, you're looking at the dispersion in the context of the mean. So the dispersion here and the dispersion here are identical, but the clinical implications are very different. If you're simply looking at TOR, you would know that the effects vary by this much, but you wouldn't know whether it looks like this or like this. And that's why I think it's important to actually use the prediction interval. The second reason is that if you try doing the mean plus or minus 2 TOR, and you're working with ratios or prevalence, you're going to get a number that doesn't make any sense at all for reasons I can't get into. But just in this example over here, we're back to the off-hours analysis. If I told you that TOR in this case was 0.038, it's always going to be reported in log units. And people that hear that, just like we didn't know based on the I-square value, whether we were talking about this, or this. If I tell you that TOR is 0.038 in log units, you're not going to know whether we're talking about this, or this. And the last thing is that when we compute the prediction interval, we adjust it to account for the fact that there's error in estimating the mean, and there's also error in estimating TOR. And you can't do that if you're simply working with TOR and multiplying it by 4. The next question came from Cedric Velg from Brussels. And the question is, when can we say that there is heterogeneity based on the prediction interval? From what numerical width would we conclude that the prediction interval is wide and there is heterogeneity? Are there any empirical thresholds or rules of thumb? This is a question that we get very, very often. And I think it speaks to the fact, you need to make a distinction between statistical heterogeneity and clinical heterogeneity. From a statistical point of view, if you're asking, is there heterogeneity? The question really is there any variation in the effect size? And the answer is yes, there's always variation in the effect size, because if you're pulling studies from the literature and they're based on different populations, the effect size is going to vary. So the term heterogeneity is in a sense, it's a statistical term, but when we ask, is there heterogeneity, we're actually using a clinical term. We're saying, is there enough heterogeneity so that it matters? And the question over here suggests that there might be some number that we can use. And the answer is there can't, because if we're talking about clinical heterogeneity, we're talking about something that requires context. For example, this is a meta-analysis not of an effect size, but of proportions. And it turns out that the mean proportion is roughly 17%, but in individual studies, the proportion varies from around 10% in some to about 25% in others. If I told you that this was a meta-analysis, maybe for people that are taking a flu vaccine, and the question is what proportion of them report headaches the next day, I might say that the amount of heterogeneity over here is trivial, right? Because, okay, you're taking the flu vaccine, it might keep you from getting the flu. You're talking about a headache that might last 4 or 5 hours. And on average, roughly 17% of the people get a headache. In some populations, it's 10%, in some populations, it's 25%. But from a clinical point of view, if you want to get the flu vaccine, it doesn't really matter whether your risk is here or here. There's not really any clinical heterogeneity. By contrast, this actually is not a meta-analysis about headaches. This is actually a meta-analysis of people who are in their 80s. And the question is, what proportion of them die within 1 day of having surgery for mitral valve, for a correction of mitral valve? It turns out that the mean effect size is around 0.17, about 17% of them die. But there are populations where only 10% of them die. And there are populations where roughly 25% of them die. In this case, I would say the amount of heterogeneity from a clinical point of view is enormous. Because if your question is, should I undergo this surgery? I really want to know whether my chances of dying are 10% or 25%. Over here, I might say no, I'll take my chances. And over here, I might say yes, because if I get the surgery, there's a 90% chance I'll survive. And if I do, I might have another 10 years of my life. My point is that the number, the plot looks exactly the same in both cases. But here, from a clinical point of view, there's almost no clinically important heterogeneity. Whereas over here, from a clinical point of view, there's an amazing amount of heterogeneity. So the answer is there is no number, and there can't be a number, because it's a subjective question based on the clinical implications of that. The second question is, from Lydia Green, can you recommend an article or video to watch for those of us who are not researchers? And again, as I said before, this actually is what prompted me to just give everybody access to the videos. Just send me an email at biostat100@gmail.com, and you will have access to a whole treasure trove of videos dealing with all aspects of meta-analysis. When you send me the email, just mention that you were on the webcam, whatever we call it today, and I'm going to give you access. Just since I know that we are recording this, and this might, people might be watching this video years from now, at some point, it's valid now. If you send me an email today, we'll certainly arrange for you to get access. But if somebody is watching this, a couple of months from now, things might have changed. We have a limited capacity. And so it's, just do this as soon as you can. I think those are the 2 or 3 questions that have been submitted in advance. Let me turn this over to you now, and I'm more than happy to take as many questions as people have. And in fact, I have no place to be. So I'm happy to sit here for as long as you'd like.
Okay, well, first of all, thank you so much. That was such a great presentation. I'm sure everybody agrees. And actually, I really loved your examples. And I think a few people did say that your examples were spot on and they really helped clarify a lot of these issues for them. So again, thank you so much for that.
You're very welcome. I'm planning now to take this as a tax deduction.
Maybe a discount off of your ring or your jewelry.
Just for your information, I mean, it turns out that the discount was not 50%. It was 20%, and the cost wasn't 10,000. It was substantially higher higher than that. But as a bonus, they gave me two free pairs of jeans. So you know, it's all good.
Well, there you go, consolation.
Okay.
All right, so I'm just going to take the questions one at a time. You know what I mean? Some of these might have been already like answered from you, but you know what? I think it's always good to like kind of reiterate stuff sometimes. So, but I think Ciprian, you just launched our last poll, so of the talk. So
That's
yeah.
right, and I will leave it open until the end, so people can take their time to fill this out.
Over here, I'm giving myself really high ratings.
Well, then it won't be a correct distribution.
Well, there we go. Okay.
Okay, so the first question is from Ahmed, who says, is it the same issue when using correlation as the effect size instead of the mean?
Well, yeah, let me open up an example over here with correlations, if I can. Well, basically, it works the same way, except that with a correlation, you can't simply take the mean plus or minus 2 standard deviations. You would need to open up, well, in CMA, it's going to do it automatically, but can you still see my screen?
It's not coming up right now, but it could take a minute, maybe.
Let me
No, you need to share again.
Okay, I have to share again, share screen. Okay, can you see it now?
Yep.
Okay, so in CMA, this will come up automatically. If you're using that program that you can download, over here on the first thing is you have to say what effect size index you're using. And there's a separate place for correlations. And then I click next, and I would type in, for the sake of argument, the correlation is 0.6, and the upper limit of the correlation is 0.8, and tau squared, for the sake of argument, is 0.02, and the number of studies is 20. And then the program would generate a plot that looks like this. Now notice, in the case of correlations, the prediction interval is not going to be symmetric, and the confidence interval is not going to be symmetric. And that's by design. Actually, the prediction interval for correlations is not symmetric. So if you were using, if you actually have a program that gives you the mean and the mean correlation and the tau for correlations, you should not take the mean plus or minus 2 standard deviations, because that's going to give you something which is symmetric, and that's going to be incorrect. And there are other problems with it as well. But if you use this program, or if you use a program like Stata or R, then presumably it will give you the correct answer.
Right, wonderful. That's great, such a great feature.
Okay.
And then Kate says, our cat says, with the mean, is this excluding outliers?
Okay, let me just close this over here and see if I can get back to my Zoom. Stop share. Okay, the question, I'm sorry, can you read that question again?
Yes, I think you were talking about one of your examples, and then Kat said, with the mean, is this excluding outliers?
Okay, the answer is this. Let me see if I can bring up an example over here on the screen. Okay, when the whole idea of computing a standard deviation, clearly what we're not doing when we compute a prediction interval is simply taking the lowest value and the highest value. What we're doing is taking a standard deviation based on all of the studies in the analysis, and using that to compute the prediction, and using that to compute the standard deviation, and then using the standard deviation to compute the prediction interval. What often happens with outliers is that they actually have a very wide confidence interval because they are small studies, and the reason they're an outlier is because of sampling error. What's going to happen is that when the program computes the standard deviation, it's going to give the outliers very, very little weight in computing the standard deviation, because it understands that if it is an outlier and that has a very wide confidence interval, the reason it's so far out is probably more because of sampling error than anything else. So you can see, for example, over here, when we have the prediction interval, actually the outlier is all the way over here, and yet the prediction interval only goes to this point. However, if you actually had an outlier that was a very large study and nevertheless had an effect which was way out on the side, then that study would get a reasonable amount of weight and would tend to expand the prediction interval. And the reason is, remember what we're doing when we do a random effects analysis is we assume that there's a whole universe of studies from which we're sampling, and we're trying to figure out what that whole universe looks like. If you're sampling only 10 or 20 studies and there's a wide universe, there might be some studies out there with a really, really large effect size or a really small effect size. You don't want to discard those because those are valid populations within the universe that we care about. You want to take account of them. And if they are small studies and they're way out on the side, you want to understand that might be due to sampling error. But if they are large studies with precise estimates, and it turns out that they really have a very large sample size and a very precise estimate of the mean of the effect size in that study, that tells us that the universe might be wider than we think. And you want to specifically include them in computing the standard deviation and then base the standard deviation on that.
Great, thank you so much.
Sure.
So I think this question's been answered, but do you know if RevMan provides the prediction interval or status 17?
Status 17 does. Status 17 has a new version. Actually, I think it goes back 1 or 2 versions, where they now have an entire set of algorithms for meta-analysis, and there is an option in there to ask for the prediction interval. Similarly, in R, there is an option to ask for the prediction interval. I have not seen the most recent version of RevMan, so I don't know.
Okay, great. And then
I'm sorry. Let me just say though that again, in order to use this standalone program, all you need is the Q value, tau square, the upper limit of tau square, and the number of studies. And RevMan does provide that. So if you simply take those 4 numbers and plug them into this program, you're going to have the whole plot.
That's right. So plug it into CMA when you have those numbers.
No, not CMA. CMA is a program you would have to buy. You can plug it into a program which is free. See, if you go to our, if you click that button that I showed you before, let me just go over here. Let's see, Metaanalysis workshops.com. You see right over here, it says
Michael, we can't see your screen.
Oh, I'm
You need to
sorry.
share.
I'm sorry. Okay, let me come back over here. Zoom. Oh, here we go. Share screen. Share screen. Okay. Accept.
Nice.
Okay, so if I go here to metaanalysisworkshops.com and you come over here, there's a button that says send me the prediction intervals program. You click on that, you give your email, and the server will send you a copy of the program, which then looks like this. And then you can take the data out of RevMan, simply plug it into this. It's a very nice program. Basically, as you click on any cell, it tells you exactly what you need to do. You click over here, it says enter the mean effect size, enter tau square, and so on. And then you click one more button and it generates the whole plot for you. So if RevMan does not provide that, you just use this, and as I said before, you just download it and you're good to go. Okay, so we are, okay, can you still see my screen?
Yes.
Okay, great. Okay, what's the next question, please?
Okay, well, this is a general question, so I think somebody's a bit frustrated. It says, so how should we report and interpret heterogeneity then? Or is it not important anymore?
Well, let me see if I can just maximize this because I've somehow. Okay, so should we talk about heterogeneity? The question is what you mean by heterogeneity. As I said before, when people talk about heterogeneity, the first thing they do is they report the Q value and the P value, which is testing the hypothesis that all studies have exactly the same effect size. If by heterogeneity you mean, is there any variation in the effects? The answer is yes. I mean, if you're pulling studies from the literature, we know the answer to that. So the question has to be, from a clinical point of view, how much do the effects vary and what are the clinical implications of that? And I think the way that you address that is by pretty much presenting the prediction interval and then talking about what the clinical implications would be. So if the question was, what do we say about heterogeneity? These are all different ways of talking about heterogeneity. By talking about how much the effect varies and what that means clinically. That is the way. So if the question was, do we then stop talking about heterogeneity? The answer is no, but I would shift the conversation. I think the first question that I addressed a few minutes ago was, somebody said, is there some number, some rule of thumb that we say this is not heterogeneity, but this is. If you're talking about, is there any heterogeneity, then the rule of thumb is yes, any number is heterogeneity. As soon as the effects vary, there's heterogeneity. If we're talking about clinical heterogeneity, then the answer is it depends on the context. I gave you an example a few minutes ago with the same amount of actual dispersion from a clinical point of view is meaningful in one context and has no meaning in another context. So I think what we sort of need to do is to sort of shift the conversation, in the way that we're thinking about this. Is that helpful?
Oh, I'm not sure if the person's still in, but I think it was very useful to everybody.
Okay.
So there was one question where the person asked for a reference that they could use for citing prediction intervals in a systematic review protocol, for example.
Oh, sure. Let me see if I can get back to my slides over here. Okay, first of all, there's this paper over here called Basics of Meta-Analysis. Isquared is not an absolute measure of heterogeneity. In that paper, we give the formula for prediction intervals and explain why it should be used. There is this paper over here by Intaust, Ioannidis et al. It's in BMJ Open. It's called A Plea for Routinely Presenting Prediction Intervals in Meta-Analysis. There's the paper in the Journal of Clinical Epidemiology that pretty much we've been speaking about during this talk. And that paper is, well, again, if you simply click the button, that will send you a link to the paper. I think those are probably three of the good, if you're looking for papers. We also talk about it extensively in our book, Introduction to Meta-Analysis. And we also talk about it in the book, Common Mistakes in Meta-Analysis and How to Avoid Them, which, as I said before, you can download immediately, and there are going to be references in there as well.
Okay, great. Thank you. Linda Green asks, in your experience, are community-based doctors familiar with these statistical concepts, allowing them to understand the primary literature?
I can't speak specifically about, well, I guess community-based doctors. My answer would be sadly no. I mean, my son went to medical school a number of years ago, and he was preparing to take the boards. And as part of that, he paid thousands of dollars to listen to these lectures on the internet, preparing him for the boards. And some of them were about statistics. And I was listening to what they were being taught. And after doing that, I decided to go back and revise my course to assume less understanding on the part of the physicians. A lot of the people that take the course are physicians. And I realized that while it's very important for me to always pitch my talks at an appropriate level. And I realized that there were people attending the course that didn't understand what a p-value was, that had never heard of an effect size, that didn't know what a risk ratio was. And so I try to always go back and sort of bring everybody up to speed and use examples that are going to be accessible to everyone. In my experience, many physicians are not properly trained in statistics. As a matter of fact, I had surgery a couple of years ago with a really, really nice surgeon. I've become friends with him since then, a brilliant man. And he said to me, you know, the one thing he felt badly about is that when he was in medical school, he was working, 20 hours a day. And so he decided to sleep through. He always attended the statistics course, but used that as a time to go to sleep because the other courses about surgery were much more important given what he was going to be doing. He said he felt badly about it because it turns out that, he's doing research now and it would have been very helpful to him, but he said he just didn't have a choice. So in my experience, physicians, they're trying to learn how to save lives, and among all the other duties that they have, statistics generally does not come near the top. So that's been my experience, sadly.
Okay, thank you.
I think, which is one of the reasons that it's so important to present these things in a way that non-statisticians can understand it. If you give somebody the prediction interval, it's hard to misunderstand that. It's it's sort of black and white. If you give them Isquared, nobody's going to be able to make sense out of it.
Yeah, agree. So I think Jordana asked why do we assume a normal distribution for true effect sizes?
It's a very good question. And often it's not a plausible assumption. You really sort of need to go back and let me see if I have this over here. Okay. I'm going to open up this. See, for many things, if we're talking, for example, about, let's say, the impact of an antidepressant on all different types of populations, many things in the world are normally distributed. We assume a normal distribution in general when we're doing a primary study, and we generally assume normal distributions when we're doing a meta-analysis. But she's absolutely right. In many cases, it's not a viable assumption. And one of the points that I didn't have time to make, but let me go back and use this as an opportunity to make it now. This paper over here by Intout et al. What they did was they went back and used prediction intervals, and they said that they went through, I think, about 150 papers, 150 meta-analyses, where the meta-analysis was statistically significant, showing that on average the treatment was helpful. And that in some very high percentage of those, I don't remember what it was, but it was a very substantial percentage. It turns out that there were many populations, if you compute the prediction interval, it also includes many populations where it would appear that the treatment is harmful. Despite that, and people often don't understand, they say, well, if the effect size is statistically significant, that must mean that this treatment works in all cases, and it absolutely does not mean that. You can have an average effect that falls on one side of the null and still have many that fall on the other side. We're talking about the precision of the mean versus the dispersion of effects, as we saw in the TOSO example earlier. Now, the problem, first of all, I'm very happy that they published this paper because I think it alerts people to the idea that we need to look at the prediction interval. But I think the mistake that they made is when they computed the prediction interval, they assumed that the distribution was normal, and it won't always be normal. And that's why over here, let me go back to the TOSIL example. Can you see my screen?
Yes.
Okay, so if I'm going to go back over here and open up the TOSIL example, and I'm going to run the analysis, and I'm going to sort this from low to high. In this case, if I plotted the effects, and I can plot them, using a raw difference in means. The zero value, the null value would be over here. And I said that anything to the right of this indicates that there's harm. But I was concerned, let's say for the sake of argument, that this is not really, this does not follow a normal distribution, that at one extreme it has no effect at all. And there are many cases where it is beneficial. If we assume a normal distribution, this curve is going to extend into the danger area. It's going to extend into the area and tell me over here that there are populations where it's harmful, when that might simply be because I'm assuming a normal distribution, and that's not the case. For that reason, whenever we have a prediction interval that includes both beneficial cases and harmful cases, I think it's imperative to go back and actually look at the data. As you can see over here, let me just change the scale over here so that it's a little bit easier to see, that there actually are 1, 2, 3, 4, 5, 6, 7, 8, 9 or 10 cases where the effect size is in the harmful range. But more to the point, there are 1, 2, 3, and probably 4, which are harmful and statistically significant. So what this is telling us is that there really are, at least I'd say, probably 4 populations where this really was associated with an increased risk of death. Now, altogether, we have what, 23 studies, and there are 4 where we clearly see an increased risk of death. And, if you add these as well, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 out of 23, where at least the effect size estimate showed an increased risk of death. So I have both of them. First of all, I can now begin to understand. What I'm saying is that what we're seeing over here maps back to what we actually saw in the data. There are clearly at least 3 or 4 where there really is an increased risk of death. And if we're simply, based on the p-values, and if we're just looking at the effect size estimates, we see an increased risk of death in roughly 1/3 of the cases. And therefore, I felt comfortable in saying that what we're seeing over here maps back to what we saw over here. But the point, and that's why I use this particular example. But the point that the questionnaire is making is a very valid one. I think if you go back and look at the paper that Inhat et al. Published, there probably are cases where the prediction interval includes harm, and that is in part because they assumed a normal distribution, which might not be the case. As long as I'm addressing this, let me make one additional point. When we compute the prediction interval, the formula that's used expands it to take account of the fact that we might be underestimating the standard deviation. So the actual distribution might be wider than the one that we've estimated. When you have 27 studies in the analysis, that expansion is trivial. But if you have only 3 or 4 studies in the analysis, that expansion is quite dramatic. So you have to understand, if you're computing a prediction interval based on only 3 or 4 cases, it's going to expand the interval with the goal of ensuring that the prediction interval actually includes roughly 95% of the true effects. And in that case, what you're getting is basically a very, very conservative estimate. And I would argue one that really is not informative at all. And that's one of the reasons that I would not even present the prediction interval unless I have at least 10 studies in the analysis. One reason that I would want to have at least 10 studies is because with fewer than 10 studies, our estimate of the standard deviation is notoriously poor. And the second reason is that with less than 10 studies, the interval is going to be expanded until it's basically inappropriately wide. I do want to point out one other thing, however. People sometimes say, well, in that case, if we have only 3 or 4 studies, rather than using the prediction interval, we'll use I-squared. The same issue with reliability that applies to the prediction interval also applies to the same extent to I-squared and to tau-squared and to tau and to everything else. So if we don't have enough if our estimate of the prediction interval is not going to be reliable, then for the same reason, the estimate of I-squared is not going to be reliable, and the estimate of tau is not going to be reliable. The difference is that if you have an estimate, if your estimate of I-squared is not reliable, it really doesn't matter. So it's not really telling us anything useful anyway. If you get it wrong, it doesn't matter a lot. By contrast, the prediction interval is a useful measure. And when you say to somebody, if you say to somebody the effect size varies from here to here, they understand what that means, and therefore it's important to get it right. So it's ironic, that it's more important to get it right if you're dealing with this, because over here, your answer actually matters. Okay, I hope that's helpful. And if it's not, please, just let me know. I'm happy to try to elaborate more.
Okay, thank you so much.
Yeah.
Somebody asked, what is the H-square?
Okay, if you go back to the original paper that Julian and Simon wrote, they were trying to come up with different ways of quantifying heterogeneity. The problem they were dealing with at the time was that the way that people were addressing heterogeneity was simply by looking at the p-value. And the p-value, as bad as I-squared is, the p-value is even worse. So they said, we're dealing with studies in the Cochrane library. Many of them have very similar amounts of sampling error. And if they have similar amounts of sampling error, we can say of the variation that we see, what proportion is real. Within that relatively limited universe, there would be a high correlation between I-squared and the actual amount of variance. And they came up with various ways of trying to quantify this. I think whereas I-squared is the ratio of true to total, I think H-squared is the ratio perhaps of true to error or something of that sort. But I very, very, very rarely see it used. I actually, I mean, I don't remember what it means. I suspect most other people don't either, but it's some other way of trying to talk about the ratio of these different parts. That's all that it is. And
Okay,
I-squared sort of took off, whereas H-squared didn't.
Yeah, definitely. Okay, so we'll take this as the last question. Abdullah just asked, what is the minimum number of studies do we need to include in the meta-analysis to get a reliable estimate of the PI and I-squared?
Okay, again, I think there's no rule of thumb. My basic feeling for a sense of scale is that anything less than 10 is probably not going to be terribly useful. However, let me put a big caveat about that. If you're dealing with, there are different types of analyses. In some cases, you can imagine we're looking at a new drug and people are trying to figure out whether this drug is effective or not. What they generally will do is work with populations that are most likely to benefit from the drug. So the populations are going to be very similar to each other. They probably will use a similar dose of the drug. They might measure outcome in the same way. So you might end up with a pool of 5 or 10 studies, which are all using very similar populations and very similar methods. And the expectation would be that there's going to be very little heterogeneity among those. If you actually have studies where theoretically, conceptually, you expect the effect size to be very similar among them, and then additionally, empirically, there appears to be very little variation among them, then you probably can so the prediction interval is going to be very narrow. It might be okay to do that with only a handful of studies. On the other hand, if you're dealing with populations which are very diverse, and therefore you expect there to be a lot of variation, you probably want to have a minimum of 10 studies to get a reasonable estimate of tau square, and probably more than that is even better. And let me give you an analogy to that. Let me go back to the case of the kids in school. Let's say you go into this classroom, and let's say that the kids are being tracked. I'm not sure if you have that in Canada, but the basic idea is that all the kids within a classroom are very similar to each other in performance. So all the good kids go into the A level, and all the kids who are not quite as strong go into the B level and the C level and so on. So you go into a class and you're trying to estimate the mean score on this test. And in this class, because the kids are all very similar to each other, maybe the average score is going to be 50, and all of the kids, if you actually knew their score, are going to be scoring between 40 and 60. It's a very narrow range. If you go into that class and try to estimate the standard deviation of scores, and you're trying to do that with only 5 kids, you might get a reasonably accurate estimate of the standard deviation, because you can't go wrong by very much. If all of the kids actually score between 40 and 60, your estimate of the standard deviation can't be off by very much, because you're not going to be able to locate any kids with a score lower than 40 or any kids with a score higher than 60, because they don't exist in the class. And since you're pulling from such a narrow distribution, even if you have only 5 kids in your sample, you might be able to estimate the standard deviation with a reasonable amount of precision. By contrast, if you're going out to a school which is not tracked, and there are kids in that class that have scores close to 0, and kids that have scores close to 100, and you're going to try to estimate the standard deviation of scores with a sample size of 5, that's going to be incredibly unreliable, because the standard deviation might be 20, but you might happen to grab, a bunch of kids, who just happen to have scores that are similar to each other. You might estimate the standard deviation as 5 when the actual standard deviation is 20 or 30. So how many kids you need depends on how consistent, on how homogeneous or heterogeneous the class is. We have the same thing in a meta-analysis. If you're doing a random effects analysis, but you're drawing from a universe of studies that are all very similar to each other, you might be able to get a reasonably reliable estimate of tau square, of I square, of the prediction interval with only a handful of studies. On the other hand, if you're drawing from a much wider universe of studies, then probably anything less than 10 is not going to be reliable. I should point out, I mean, one of the things that Julian talked about when he got up that time in the workshop, he started explaining that people don't understand how unreliable estimates of I square might be. That if I square is estimated as 50% in a sample size of 5 studies, the actual value might be 0% and it might be 100%. So, but that applies also to the prediction interval. If you have only a handful of studies, the estimate's going to be very wide. And that's one of the reasons, as I said before. Let me open up this program over here. This is the program that you can download. And let's say we're talking about I'm going to open up the file that I had a minute ago, which was called the TOSIL data. And I'm going to say, we said over here that the distribution of effects looked something like this. And that was based on, again, this is the prediction interval, and it's being expanded to take account of the unreliability in our estimate of tau square. Let's say I go back to data, and instead of saying that we had 23 studies, I'm going to say that we had only let's say 5 studies. Look what happens now to that interval. Look at how much wider it gets, because it recognizes that our estimate of the variance is way unreliable. And therefore, while we estimated the variance, the prediction interval, we're estimating a prediction interval using numbers which themselves are terribly unreliable, and therefore it expands this to cover them. Okay? But so the formula for the prediction interval actually takes account of that, whereas the formula for I square does not take account of that. Okay, does that answer the question?
I hope it does.
Okay.
So actually somebody said the same thing, but for network meta-analysis, and I would assume that would be in network meta-analysis, the same rules that you're talking about, but for each comparison in the network.
I suspect that it would be. I have to admit that I don't understand enough about network meta-analysis to be able to speak about it with any authority. I mean, from a general, if the question is, it's the question, do we want to build a prediction interval around these various links, the various effects? And if the question is, in doing that, do we have to allow, do you want to have at least X number of studies in each one? I think the same general idea applies, but in a network meta-analysis, I suspect it would be much more difficult to compute, because the precision with which we're estimating any of these things is much more complicated. And so I think the general idea applies, but how you would apply it in that case, I wouldn't have any way of knowing.
Okay, well, thank you so much, Michael, and we really enjoyed your presentation. Is it okay if I send you the questions to everybody, and then
Absolutely.
I think there's been a few people who have requested that, we could lump, questions together that are, similar and stuff. But
what I will do with the questions is, first of all, I'll try to answer each of them individually. I'll try to answer each of them, like maybe I could just put together a Word document where I'll try to address each question, or you know what? Maybe I'll put together a video where I'll try to address these. And again, I really encourage everybody, if you send me, I don't have access to your emails. If you just send me a note at bias.100@gmail.com, and then I can include you in this group. And then when we talk about these, we can basically continue this conversation for as long as you'd like. And I can come up with examples that address your particular questions. And again, you'll have access to the videos for free. So yeah, it's good.
Okay, thank you so much. Yeah, this was a great presentation.
Thank you. Let me thank you again, both Ciprian and Carol. I ran into Carol at SRSM. She actually stood up and announced that she was looking for people to talk, and I said, that's me. Thank you very much for the invitation. Nice to see you again.